right, so welcome everybody to Value First Expert Interviews. Today we have no other than Tom and Mary Poppendieck. Did I say that right?
You said it perfect.
Yes. Need not much introduction, I think, in this community. Now, so first of all, welcome. Happy
Good to be here.
To have you here.
Yes.
Now, I'd like to start off maybe somewhere where other people don't start. Quickly, each one of you. Could you take me back to when you were kids, like 10 years old, something like this?
Yes.
Where did you live? Can start with Mary.
I lived summers in Milwaukee.
Yeah.
I lived winters in Milwaukee, a suburb of Milwaukee. Summers on a farm about 25 miles away that my father inherited.
Yeah.
I had 10 brothers and sisters. I was the fourth oldest and second oldest girl, and we had lots of younger kids that we took care of. The older half took care of the younger half. And my father, when he inherited some money, he bought a farm so he could come into work every day, but we could run around on the farm all summer. And so when I was 10, yeah. my youngest sister was just born, because my youngest sister's 10 years younger than I am.
Yes, okay. So then you had a little...
So it's quite a family.
Yeah, and they also lived on the farm?
We all lived together, and summers oftentimes aunts came and helped out a little bit, but pretty much we just ran around the farm. Winters, we went into school. Our school was right across the parkway, so we walked over to school every day, across the street, in through the park, and that was our life.
Yeah, this kind of runs into my next question. What did you like to do? Like as a hobby, an interest, sport, activity?
At 10?
At 10, 11, something like that, around that. As a kid, as a child.
Read.
Read, yeah.
I read books about horses.
Yeah.
Took care of my little sisters.
Yeah.
I like to cook.
Cook also.
I was starting from even before I was 10, I was the main cook at dinner time for our family.
At 10?
For our large family.
Wow.
And I started out by doing the grocery shopping. I'd walk to a grocery store about a mile away, and I'd call my mother when I was done. She'd come pick up me with all the groceries. And oftentimes I would cook the dinners during the week.
And you're still cooking?
Oh, I love to cook.
And then one last question before we'll ask Tom. Did you have somebody as 10 years plus minus a few as a child that was a great influence to you? That influenced you?
Oh, my mother.
Your mother.
Absolutely, my mother. She was like, anything she said we did, I thought she was really cool.
Cool mother, that's
yes,
nice.
Really,
with so
really,
many kids.
Really,
she
really
could have
was
been
impressed
stressed
with my
out,
mother.
right? And just like...
Nah, she wasn't. She's very good at handling 11 children.
All right, thank you. And really the same, Tom, where at around 10, where were you?
60 years younger.
60 years younger, yeah?
Hard to remember. Grew up in Milwaukee.
Yeah.
I remember, some of the earliest things I remember are my father building our home. He was a math teacher at a technical high school in Milwaukee.
Yeah.
And among the subjects that were taught there were plumbing and electricity and carpentry and such. And so he had all the assets among his friends that were needed to design a house. And he did.
And build it.
Design and build a house, yes.
Yeah.
And at that point I was like 3 or 4, so I mostly got in the way.
Yeah.
But my father and my mother's parents, and occasionally his parents, would come over and did almost all of the labor on the house that was permitted. A decade later, I was old enough to help, and then we put a porch on the back of the house. And he overrode a number of design decisions that would have made it better from my perspective. But we didn't have a farm, but we do go camping a lot. Family camping around the state of Wisconsin. We took one long trip around Lake Superior and Lake Michigan and back home. And somewhere in that time I remember that my father was now assistant principal, and he was responsible for planning the schedule in the high school. And he was asked by IBM to be a test site for a software package that would do the scheduling by computer.
Hold on. So the software package.
Yes.
How old were you at this point? You're getting a little older now, or you're still 10?
Oh, this is somewhere 10, 12,
Yeah,
somewhere
okay.
in there.
They're already doing software packages.
His father was.
My
Yeah,
father
but-
was
but,
testing it out.
There weren't that much software back then.
You're
Well,
right. This was
yeah. At
that
very
point-
early.
Very early. That's
At
what I'm
that
picking
point,
up.
the input method was punched cards.
Right.
And the initial effort was taking big trays of punch cards with each student's requests for what they wanted, and each teacher and what period it was in, and he would sit down in the porch and pull out cards, make a stack for each student as to what course they would be enrolled in, and then take it down to the county government computer center where they had card sorters
So he would move the data in the form of
in
cards
the form of cards
to another machine.
to a card sorting machine.
Yeah.
They take all the student decks and sort them by class, and that would print out the class lists of printer, and then sort it back to student, and that would print out the student's schedule. That was the first iteration. The next iteration,
In the first iteration, your father actually did the assignments.
yes,
Right. Right.
yes.
But you were observing
And it
this.
still worked. Well, I helped. And that worked very well because there was a lot of knowledge about the intricacies of complex multiple period classes for shop that he had been aware of because he'd been doing it for a long time. And then they tried to put it in a computer down. So we went down to a computer in Chicago of a 1401. It was a really hot machine at that time. I don't know if you've ever seen a 1401.
Picture.
But the cards instead got read into a magnetic tape, and the tape went into the computer, and the computer chugged away for a couple of hours, and it came out with a program, which Dad then went in and fixed. Not the program, but the results. And I guess eventually they got it kind of working, but the first iteration was kind of clunky.
So this is my next sort of thought. Like, so, you know, I'm seeing this data being handled with cards and tapes, and you know, we talked about earlier, the speaker earlier here was talking about quick iterations, right? And seeing what what was done right away.
Yeah.
Yes. Now, what do you think the time savings were for doing it with this computer systems rather than just, I don't know,
Negative.
paper and yeah. So initially, probably
It probably took longer.
probably took longer.
Eventually, the results were probably better.
Well, we know a little
Right.
bit about what eventually happened.
When you take it to a ordinary high school that has all classes being single period and meeting the same days every week, it worked a lot better and a lot quicker.
Yeah.
But they chose the most difficult scheduling problem because if it would work there, it would work other places as well.
So same question, but I think you already touched it. So this was a big influence on your life as a person at this time, seeing these computers and
Well, shortly
helping?
after that, I decided I wanted to have a computer.
Mhm.
So we had a shop in the basement, And I decided, well, let's see, what can I do in this shop? I figured I could do a relay. So I would wind wires around a nail and try and fabricate some armatures by cutting some sheet metal and trying to make a pivot so it would switch.
Yeah.
And that's about as far as I got.
All right. So, but you actually started making your own.
I never
switch
got much
computer.
further than trying to get the single relay built.
Yeah.
Did you ever get one built?
That worked very well, no. But
So-
then in high school,
Yeah. That was my next.
I did science projects
Yeah.
for the local science fair, and by senior year, I won a trip to the National Science Fair for a project studying the dynamics of air bubbles in water of various viscosities and surface tensions,
Okay.
and actually got a trip from the Navy to an event that they had down at the Naval Air Station. So that was fun.
Yeah.
And went on to major in physics at Marquette, because one of the prizes I got from the science fair was a full tuition to Marquette University. And that's where I met Mary.
Mm-hmm.
Mm.
So I was
How
in
did you end up there?
How did I end up there?
Yeah.
Well, it was close to home. And my brothers could go to any college they wanted to, but the girls in their family, which were most of the 11 kids were girls, my father said he wouldn't pay for us to go away to school because the boys needed the education and it was just like, it wasn't so important for us. So I went to Marquette University, which was between my house and my father's office. It was like easy, and he was actually doing some buildings for them as an architect. And I went into the physics class to take physics because I thought it was an interesting subject. And the professor mentioned something to this guy, Tom, about, oh, good to see you after that neat science project that you did. And then a little bit later, we were supposed to choose science partners. And I thought, well, I want that guy that did the neat science project for my partner. So the rest is history.
Sweet. So, and then where did software come in? You started with software as a kid, and then to physics. And what about you, Mary?
My first job after college was working at Bell Telephone Laboratories in Naperville, Illinois. And what they were doing, and my job was involved with, was the number 2 ESS, which is electronic switching system, the second telephone switching system ever built in the U.S. It was built out of mostly individual components and very small ICs, some of the very most primitive ones. And this was an amazing machine. A lot has actually been written about it. I worked on it. What I was doing was the programming after that was completely duplicated. So let's start here.
Yeah.
The switching telephone system was to replace relays. The relays they failed, but it only affected one line. If a computer failed, it brought down a whole thing. So they said, we have to make computers that are as reliable as any telephone switching system, or we can't use a computer. So the design goal here was 2 hours max outage in 4 years. And so
40.
it was 40. And 2 hours out in 40 years. And they achieved it, they did, by at least extrapolating achieved it. I don't think it ever ran for 40 years. It was duplicate computers, and if one of them went bad, then it would decide which one was bad and kick it out. And then my job came in that this happened a lot, so you had to quickly repair whatever the problem was. So I wrote some software that would go through cards, find which card was bad on the computer that was bad, and then which components on the card, and then print out a message to the technician to change this component. So that's the software. I was taught to do software. I was programming in a very interesting assembly language at the time, and wrote the code that diagnosed the cards to find out where the sick component was. And I test my stuff by making a component sick in some way and seeing if it found it.
Now, So you mentioned you use redundant systems for the hardware, right? To get this very high reliability. Now, I haven't seen much redundant software. I keep seeing redundant hardware, but
Well,
not
the
redundant software. Do you have any
software had to go
experience?
through and decide which hardware was bad. So it was
Right.
very software intensive. Most of the software in that system was designed to keep it up.
Right. But have you bringing back in even into today's world, have you seen
What do
any
you
or much
mean-
redundant?
What do you mean by
complete-
redundant software?
Yeah, like you have, just like hardware, where you could have two software applications or systems that are maybe built by separate teams, not using the same anything, that do the same thing. They check against each other.
The space shuttle.
Or, right, space shuttle have redundant software, right?
They had 5 different computers, all
Yeah.
of which did the same job. The software for each one of those computers was developed by a separate team using different methodologies.
Right.
And then they compared the results of the different computers. And if one of them went bad, they took it out.
Yeah.
If 2 of them went bad, now they have to start fixing something. If 3 of them go bad, they still have redundancy.
Right, fantastic. So I think I hear very little of this technique, but I think the more
I don't
the more
even
we
hear
ma-
about redundant
Sure.
hardware anymore.
Well, yes and no, right? An airplane has 2 engines, or 3 or 4, right? So
This is true.
So this is like redundant hardware.
But you don't see computer systems. There used to be Tandem Company that had redundant
Right,
computer
Tandem,
systems. They
exactly.
didn't make it
Right.
because they weren't. There came a time when people decided redundancy wasn't necessary
Redundancy
anymore.
has been replaced by resilience.
Ah,
The resilience means that you can detect problems very rapidly and recover from them so rapidly that nobody even notices the problem.
exactly. Okay.
And that is what all the big cloud systems do. They are made up of huge numbers of very unreliable computers.
Right.
And the whole
And everything's duplicated.
point is
All the
that
storage.
anything can and will fail, but both the operating environment and the application software is written in such a way that it will detect and recover instantly. It'll put in a new instance of a service.
Right.
It'll do whatever it has to the point where, for example, Netflix is able to recover from the total failure of an entire Amazon region, and the subscribers will never see the difference.
Right.
That's pretty awesome, that
That's pretty awesome.
10,000 servers can go down and the subscribers never even see it.
So Google pioneered the Google file system, which basically writes in triplicate lots of little pieces of everything that they know, in lots of little places. So there's a triple copy of everything on the internet, and when one of them fails, 2 of them are left,
Right.
and they just kick off the disk. They run on lots of cheap hardware, not expensive stuff. They were the first company to do that, and they said, stuff's going to fail. We're
Right.
going to get big, we're going to let stuff fail. As soon as this disk is out, okay, fine, we got 2 other copies. You kick that one out, another one gets spun up automatically, and you get your triplicate again. And all you do is alert the maintenance guy to come in and pull that disk and throw it out.
Right.
So it's still
Is-
redundant,
Is redundancy of
but
data.
the whole point is
Oh.
resilience.
The hardware doesn't have to be redundant. All you have to do is keep the system running.
Right, but what you explain, as I understood it, is a redundancy of data. So you have
Right,
you
because
have
the
several
assumption
copies
is
of the data.
that hardware is not ever going to be reliable, so why even
Right.
bother try?
And
Right.
multiple copies of all the services.
Right,
There isn't even an attempt to make hardware reliable. There's every attempt to just deal with the fact that it's not reliable.
right,
And all the systems, all the big systems in the world have made that leap, or they don't work, or they don't scale.
Right.
At certain scale, stuff is going to fail. And if you haven't figured out how to accept it and move on, recover really fast, instead of trying to be perfect, you can't scale.
Talk about failure. Tell me, did you ever do, either one of you, a big mistake? Like you were in a project and you completely failed, or something you did in the project or life, which was, hopefully you learned something, but we can talk about that afterwards. But, we all like to talk about all the great things we did, right? So, but a big failure that sort of put a mark in you as a person.
I'm not saying that I never failed. I'm saying that my attitude all my life has been to make the best of whatever situation I'm in.
Right.
So if things went wrong, okay, well, it was time to figure out how to fix it. It was not time to worry about what caused what went wrong, but to try and move forward.
Yeah.
So I can't think of anything. Can you?
No, I don't either. Not that everything has been a
No, clearly not.
huge success.
I understand.
But I don't remember the things that weren't.
Selective memory. We all have.
Yeah, how about that?
I have selective memory too, that's for sure. All right. Now, these days, Agile in its various forms are all over the place. It's hyped, it's sold, it's used for good and bad. Now, but you're sitting with, are you about over 140, are you 140 years combined
Something
life
like that,
experience?
yeah.
Yes. So, help us out a little bit. What are we doing wrong?
Okay, so in many senses, Agile isn't anything new. If you go back to when computers were first young, the idea that when I first learned to program as a software engineer, working for 3M, we had small teams. The teams sort of worked together to bring up very sophisticated process control systems. And we worked with very immediate feedback, and we didn't have this, somebody writes all of the requirements. Our requirements were like 5 bullet items. Put a control system on this process. Make sure that it works. Use the latest technology. Here's the startup date. And it's going to be maintained by the plant engineer, and by the way, the operators better find it very convenient to use. And that was it. And we knew what we were supposed to do. And everything else was engineering. Nobody tried to tell us, okay, that means this in detail, or okay, here's what you got to do this week, or anything like that. It was high level, and then we had our control engineering organizations. All the managers were control engineers. They know what it meant. There were senior engineers that helped us junior engineers figure things out, and we met the deadlines and stuff worked. And
so you had let's call it mentorship quite strong in that.
Well, okay, so an engineer, I don't care what kind of engineering it is. You don't come in knowing how to do engineering in detail, because engineering is something where there's a lot of experience involved. So every engineering discipline has you've got some junior people, and they learn from the senior people, and they specialize in particular areas they get in on. Doctors are the same way. So if you think of engineering as a professional occupation, lawyers are the same way. The lawyer first out of college doesn't know anything very much, and eventually they learn under the guidance of more senior lawyers or partners, and then they become specialists in particular areas. And engineers the same way. And so that's kind of how it worked. So we got projects that with constraints that we always met. The idea that software projects fail was an interesting concept to me, but I didn't ever realize that they should, or that they did. Because when we had a charter, we met the deadline and the stuff worked. And I think it's because nobody ever told us how to do it. They only told us the constraints. They told us when it needed to be done, what it needed to control, and the expectation was that it would work. And there were, extra people or senior engineers or whoever around if there was any particularly big problem. So that's the way that we did engineering when I learned how. I happened to be the person that did computers, but that's the way our engineering organization worked. So if you think about that, and then you think about, then I learned that there was these things called projects with work breakdown structures and tracking of tasks that were assigned by project managers and all this nonsense, and that they failed most of the time. I'm thinking, huh? Yeah, help me with it. I don't get this concept. And I actually never have gotten this concept. I mean, we did projects, we installed great big process control systems, but not with the techniques that people currently say, oh, here's your cost, here's your schedule, here's your scope. We had a cost, we had a schedule, and we had 6 bullet items of our objectives. We always met the cost and the schedule, always. It's just that we did our best efforts engineering towards completing the work that was necessary to make it work right. So I think that I ran into this thing called waterfall, never actually used it. After it was a big thing in the late 1990s, I had been in a manufacturing plant heading up the IT department there. And when I came sort of back in, and then I did some engineering lighting systems that were non-software. And then I decided to get back into what was going on in software, and I found that they were doing this crazy stuff called waterfall. And I had, what? How could that ever work? It turns out it didn't. And so then, because waterfall didn't work, and waterfall seemed to be the thing that people were supposed to do, they learned that it didn't work, and then they went back and learned the way we used to do things was actually a better way. And to some extent, that's how I think of Agile, as relearning the history of the way software used to be developed. And the problem with Agile is that it's gotten some things that you're supposed to do to attach to this brand of Agile or that brand of Agile. And I don't think that's right, because I don't think that in every context, in every world, and so remember, software does everything from websites to firmware that controls automated vehicles. There's lots of stuff spanned in that environment. Software has a process which requires an awful lot of intelligence and people understanding how to deal with a complex world and how to give instructions into various pieces of equipment or various other areas so that it works. Software can involve a lot of design, especially when there's users there that are going to use it, so there needs to be good user interaction design. But that idea that there is one single mandatory process that has these things you better tick off if you're not doing it right is, I think it's kind of silly.
Agile has 2 groups of components. One group of components are the technical practices. The main components of extreme programming, for example, are very effective, powerful, and they remain relevant today.
Continuous delivery.
But they have evolved into the whole realm of continuous delivery and DevOps, which is dramatically more powerful. The other component of Agile is basically project management components. Those, I think, have shown that they don't work very well. They don't make terribly much difference to the organization deploying them, because project management is really not what you're all about. What you're about is solving problems to make a difference for the organization, and that is in part a engineering task to the extent that the solution is technical. It's in part a organizational architecture policy task, and often you need both components working effectively together in order to address the problem that the organization has or the opportunity it's trying to pursue. Agile still separates deciding what things to pursue from the pursuit. And what I think has replaced Agile in the leading organizations today is recombining the policy, the domain expertise, the technical expertise, the ability, leveraging DevOps, continuous delivery to do rapid, inexpensive experiments, lots of tools that don't even involve software to do experiments and learn rapidly what is going to address the problem most effectively. And this is a total abandonment of the concept of a project. It's more a rapidly evolving product. And that, I think, kind of obsoletes what most people think of as Agile.
Interesting. I like it. Now, if if let's take you back, not maybe 10 years old, but maybe a little older. You know, you're a teenager, maybe early 20s, and you're starting your career, maybe in software, maybe in systems. What would you recommend that they study and learn and dive into?
So we have granddaughters in college. So if I definitely can think of one just graduated and one is just starting or entering second year of college. And if they wanted to get into an environment that dealt with software systems, I would recommend that they get into engineering of some sort and learn problem solving. The problem with computer science is it's not about problem solving. And the problems we attack with software are really, really in need of good problem solving skills. And there are definitely some engineering techniques that need to be learned and leveraged when you do seriously good software. But if you're going to do software in and of itself almost never has any value. The thing that software does is it brings value because it does something to something else. And the problem domain is not typically in the software domain, occasionally, but not usually. It tends to be in the domain that you're trying to solve. It tends to be outside of the software domain. And most people who develop software are solving outside of the software domain problems. And they need to understand those kinds of problems and how to attack them and how to think about them and how to be engaged in their solution. Otherwise, they just have somebody else do what the interesting stuff, solve the problem, and just tell them what code to write, which is not software engineering. It's like kind of boring.
Right. So when you say get into engineering, you mean not software engineering. You mean more traditional engineering.
Well, you
of
need
some
to leverage
discipline.
software engineering to do an awful lot of things.
Right.
But the question is, if you're learning software engineering, it would be good to learn it against a domain.
Right.
How about how to control robots?
Right.
That would be cool. Okay.
Right.
How about how to create really, really interesting engagement stuff on a screen with a person?
Right.
The psychology behind that. How about if you're dealing with hospital systems? What are the major problems in hospitals that a software system might attack?
Right.
And how might it do something? So you need to learn how to take this tool that you're learning and learn well how to use it against a problem that typically is not a software problem, and become engaged in some field, preferably not every field, but one or two fields out there that you become really good at, whether it's legal or whether it's architecture, it doesn't matter. All of these fields need good software systems, and they're going to be designed not by software people, but by people who understand the domain problem. That's where the fun is.
Yeah.
And so that's where you would want as a student to become good at, is solving problems in some technical domain. And oh yes, by the way, today software is one of the major tools you have. Now if you go into some of the really interesting stuff in putting together, say, a very sophisticated data center, or the Google file structure that came out in 2003, those were very seriously computer science problems. If you look at the stuff behind the way Amazon initially put out its services, those were seriously important computer science issues, and they used computer science experts. But by and large, the jobs in software engineering are solving problems that are not software problems. They're solving other kinds of problems. So I would encourage for the largest opportunity to do interesting stuff is to become good at solving problems in technical domains.
Anything to add to that, Tom?
Well, I started out as a high school physics teacher, and then I taught as a physics professor at a university for a number of years. And in the 80s, I moved to Honeywell, where the major project I did was a product data management system that made a very large impact on the engineering organization that developed navigation systems for commercial airplanes. You probably are still flying on those systems. I can assure you they're very safe. But part of my time there, I was a supervisor, and when I needed to hire someone, I would look first at electrical and mechanical engineers, and only if I couldn't find one would I settle on a computer science
Right.
person, for exactly the reasons that Mary stated.
Yeah.
The key thing is problem solving and experience in solving problems. The techniques are changing so rapidly that anything else that you learn is going to be obsolete very, very quickly. We're using tools that are so much more powerful. The abstractions that we engage in today compared to those that were taught to university students 5-10 years ago are so far beyond it that the ability to learn continuously the skills that you need to address the problems you're encountering now is the primary thing, not what you studied 5-10 years ago.
Right. I think that's why you're both relevant today. I mean, you could easily not be at your age, but you are the leaders today because you are taking it away, a level up from the specific technology to the problem solving and engineering and methodologies, etc. Which we all get to enjoy, so that's great. Now, one last thing. You were talking earlier a little bit, hinting to SpaceX and Elon Musk, who is, for me, very, very interesting. I mean, what the guy can accomplish
Pretty amazing.
is just amazing. So I'd like to sneak that in. Anything you observed or have read about, or I don't know how you get access, for how Elon Musk is succeeding wildly.
Okay, so I was recently asked to give a talk at a company that's doing very sophisticated warehousing and fulfillment systems. And their technology group, and they're also doing web front ends, but their technology group was not interested in saying, oh, let's have lots of independent teams and do agile, because they understood that when you get into sophisticated hardware software systems, which is the kind of stuff I did, it's way more than just put together these teams and that sort of thing. So I started studying some of the most interesting hardware software systems that I could find, and one of them was the Falcon Heavy, which just took off in February. And I can remember watching those two booster rockets landing together and saying, wow, that's amazing, okay?
Impressive.
That's amazing. Even the thought that you would land them is amazing. They were always dumped into the sea. And we'd all watched all of the failures, but they landed. Of course, the third one, it kind of didn't, but and they didn't really have any reason for this very interesting test except to test things. So they shot a car up into space because they, couldn't get anybody who wanted to put a payload on, because this was not to do something, it was to test a lot of things. So I said, how do they do that? I mean, the whole way that they develop rockets is so different than how anybody that used to be paid by the federal government and run standard projects would do it. How is it? And I found some interesting papers on systems engineering at SpaceX. And it basically said, no, the job of system engineering is to develop safe and reliable systems that are going to work. And there's a couple of ways of approaching it, but with today's modern techniques and technology, you can learn a whole lot more, a whole lot faster by having end-to-end test events and actually putting everything together and finding out all of the interaction problems than you can by imagining and tracing them and spending years writing them down and thinking about them. And we believe, and of course it cost only 20% of the price of Delta Heavy to get Falcon Heavy up there. And they had some failures, but their first takeoff was a success. And he said, we find that if we have these integrating events, it's a process called sync and stabilize. So at every 3-month increments, and that's how often they shoot off these Falcon rockets, you try a test that has already had all the subsystems tested, and now all they did was shoot off a booster rocket and see if it would land. They did that several times in the first few times.
Right.
It didn't. But one of the engineers was quoted as saying, well, I don't worry when Elton calls at the end of the day, but I do know one thing, and that is I had better know what went wrong and what we're going to do to make sure it doesn't go wrong again. Because their structure is a structure of responsibility. So they don't have a lot of engineers, but they do everything in-house. 85 to 90% of that is even fabricated in-house. And there is a responsible engineer whose job it is to own responsibility for, say, a subsystem or for the whole system, and that's fractal. So you'll have responsible engineers for subsystems. And their job is to figure out how to design it, how to get it built, how to make sure it's properly tested, how to know if it fails, that they've had the test and cameras in place to find the cause, and how eventually to make that thing work. And it's a very intense environment, but if you look at people talking about working there, they said, well, you gotta love it because you have so much responsibility so early, but you better not have anything else in your life. No family, no nothing, because it's so intense.
Yeah.
But the people that work there just love it because they're so wrapped up in their piece of that job. They understand what they're supposed to do, and they work really, really hard to come up with very, very novel, new, simple solutions to really tough technical problems. It's a ball. It's a blast. If you're an engineer, like there's few places that'll give you that level of responsibility that fast. And so I thought, okay, so that's an interesting way of looking at a big complex system instead of these web-based systems. And if you look at that, or you look at how big complex automation systems, Siemens does big baggage handling systems. If you look at their techniques, you can find out a whole lot about software engineering in a world which is also involved with hardware. So that was one I studied. And I did everything. I looked at their progress level compared against a base level of other rockets, what Glassdoor says about how the engineers like working there. And it was a lot about the engineers really enjoying the challenge and the responsibility. And just if you could be totally absorbed in something, that would be cool. Rocket science is a lot of fun. And if you think about that, when we were doing control systems, as I said, we were always on time and they always worked. And guess what? That's the same thing that's going on at SpaceX. Stuff is on time. You schedule a launch, it happens. You schedule a planned startup, it happens, okay? And you have your area of responsibility and you make it work. But nobody tells you how to do it. Nobody does the engineering for you. It's your challenge. And you've got people to ask and be engaged with and talk, and you've got a team to run tests with. But it's your problem, and it's so much fun. And as I watch software evolve to this, well, let's tell people exactly what to do, and let's have a report at the end of the day how they're coming along on their assigned tasks. I'm thinking, well, how insulting is that? I mean, if I was a control engineer and I'm designing a control system for a big roll goods process, nobody has a right to tell me exactly how to do it. That's my job. That's what I'm being paid for, to figure that out. So why do they think that somebody else should tell me all the details of exactly how to do it? That is a ridiculous concept. I never understood the concept of requirements, and to this day I don't. I understand the concept of deadlines and constraints. And if they're requirements, they can be listed on one page in 6 bullet items. And everything else is engineering. And engineering is fun when you get to work in a set of constraints with some sharp colleagues to solve interesting problems. That's just a ball. And I'd like to have more people experience that instead of the relatively simplistic and very micromanaging kinds of processes that most agile systems have.
I agree with Mary, and I generalized it a bit.
Yeah.
Hard engineering problems with physical interaction is one dimension. The other dimension is organizational process and people interaction systems. And as I mentioned earlier, this requires not just decisions about engineering, typical engineering things, but it also requires decisions about policy, about investment, about a whole bunch of different dimensions of concern in an organization. And if you're going to solve problems with these multiple dimensions, you really will get a better solution by far, and you'll engage people far more deeply if they are combined together, that people with all the expertise needed, all of the authority needed, are working together on the problem, rather than one group having a fantasy about this might solve the problem, so you go do it. And you do it and it doesn't quite work, and you may never know it because a whole bunch of good ideas were available from the people with the technical abilities that you never found out about, and they were never tried. So you end up with mediocre solutions.
Right.
And then the really smart people with the technical people go find a more interesting job, because it's not worth sticking around and have somebody that doesn't know what they're talking about telling me what to do.
Exactly.
The fundamental problem in many, many cases is architectural. Organizations that have existing software typically have an architecture that is not amenable to rapid small changes and experiments. I'm sure you've run into that many times in your work. But they also have an organizational structure, the way the teams are, the people are organized into groups, that is not amenable to that. And the response of many organizations, and the Agile movement in particular, is to come up with a process solution to what is fundamentally an architectural problem, a technical architecture problem and a organizational architecture problem. They're the same thing by Conway's law. And if you're going to fix it, you have to fix the architecture in order to have better solutions to a wider domain of problems.
All right. So I wonder, this paper, you specifically won system engineering paper at SpaceX. Is that something publicly available?
Yes, but if you send me an email, I can send it to you.
Yeah.
Or
Can I share it?
I think so. I pulled it off of the proceedings of public conference.
Yeah. So it should be.
Mhm.
Yeah.
All right. Thank you, Mary.
Thank you.
Thank you, Tom. Looking forward to hearing more from both of you as the time goes by.
Great.
And I think that's something for everyone here to learn from and pick up
Great.
ideas. Thank you so much.
Thank you.